In the video for step 4b, we performed the optimality test on the basic initial feasible solution using the modified distribution method. And as a result of that step, we found out the net cost change for each of the water squares. Now again, water squares are the squares which do not have any allocation. So if you see on the right, I have listed the water squares and the net cost change values that we arrived at in step 4b. Now the evaluation of the net cost change values indicates that there are negative values for a few squares, and the negative values indicate that the solution is not optimal and there is potential to further reduce the total transportation cost. So once we have found out that the solution is not the optimal solution, in this video we will find out how to iterate towards optimality. Now when we do the iterations, we will first modify the current solution to arrive at a better solution, and then we will use the modified distribution method to test if it is the optimal solution or not. If we find out that the solution obtained is not optimal, then we will again try to improve it and then test it for optimality and continue these iterations till we find an optimal solution. So step 1 for iterating towards optimality is to select the water square with the largest negative net cost change. Select the water square with the largest negative net cost change. Now we want to choose the square with the largest negative net cost change because the larger the negative net cost change, the more is the reduction in cost if allocation is made to that square, and thus we'll need lesser iterations to arrive at the optimal solution. Now in our case, we have two squares which have a negative value of net cost change, that is AR and BR, and both of them have the same value of -1. Now the net cost change means change in transportation cost if 1 unit is allocated to that square. So since we have a tie between AR and BR, and since the net cost change is the same, we now need to find out if there is a difference between the number of units that can be allocated to these scales. And whichever square can be allocated the maximum units, that square will be selected first. So in case of a tie, choose the square where maximum allocation can be made. Now why are we doing this? Because the transportation cost is a multiplication of the unit cost and the number of units allocated. So since the comparison between these two cells indicates that the unit cost of making the change will be the same, we are now seeing if there is a potential for allocating more units to any one square, and the one which has more potential will give us higher savings in the total transportation cost. Now in order to find out the maximum that can be allocated to each square, let's draw the closed path for squares AR and BR. So for AR, the closed loop will be AR, AP, CP, CR, and back to AR. And for cell BR, the closed path will have BR, BS, CS, CR, and then back to BR. Now next is to assign alternate plus and minus signs on the closed path, starting with a plus sign on the water square. So in case of AR, the water square is AR, so this will be plus. So AP will be minus, CP will be plus, and CR will be minus. And in case of BR, BR will be plus, BS will be minus, CS will be plus, and CR will be minus. Now in the closed path for AR, we have to reduce allocation from the squares with negative sign and add to the squares with the positive sign. Now what is the maximum that we can subtract from AP and CR? Now AP has an allocation of 1 unit while CR has an allocation of 3 units. So since we can't subtract more than 1 unit from AP, or else the allocation will become negative, which is not feasible, the maximum we can allocate to AR is 1 unit. So in case of AR, the maximum allocation is 1 unit. Now similarly for the water square BR, the maximum allocation which can be subtracted from the cells BS and CR is 1 unit. So we can allocate at the maximum 1 unit to the square BR. So BR is 1 unit. Now again there is a tie between the maximum number of allocations that can be made to AR and BR. So in such cases we can choose any of these water squares arbitrarily. So in case of a tie, choose any square arbitrarily. So in our case, let's choose the square AR arbitrarily. And now let's move to step number 2. So step number 2 says subtract the smallest of the figures from each square at the negative sign on the closed path and add to each square at the positive sign on the closed path. So subtract the smallest of the figures from each square at the negative sign on the closed path and add to each square at the positive sign on the path. So basically this is the same step as we had seen earlier to identify the maximum allocations that can be made to a square. Now note that in case we did not have a tie between AR and BR, we would have built the closed path for the selected square as part of step number 2. Now for AR, the smallest of the figures at the negative sign on the closed path is 1. So the new allocation at AR becomes 1 because this has a plus sign. The new allocation at AP becomes 0 because this has a negative sign. At CP, the allocation becomes 7 because this has a plus sign. And at CR, the allocation becomes 2 because this has a negative sign. Now step number 3 says, prepare the new transportation table and check for optimality. Prepare the new transportation table and check for optimality. Now in this video, we are using the modified distribution method for optimality test. So this is the new transportation table that we have obtained after making changes to the allocations. Now let's quickly calculate the total transportation cost for this solution. So total cost is equal to, so 5 3s are 15 plus 11 1s are 11 plus 1 1s are 1 plus 7 5s are 35 plus 15 2s are 30 plus 9 1s are 9. So this is 15 plus 11 is 26 plus 1 is 27 plus 35 is 62 plus 30 is 92 plus 9 is 101. Now again the unit cost is expressed in terms of hundreds. So we'll multiply this by 100. So the total transportation cost is 10,100 rupees. Now the total transportation cost that we had obtained using the Vogel's approximation method was 10,200 rupees. And after the first iteration, to improve the initial solution, we have reduced the cost by 100 rupees. So there's definitely some improvement here. Now let's find out if this is the optimal solution or not. But before we test for optimality, first we have to test whether this solution is acceptable to proceed with the test for optimality or not. So let's first do the test for acceptability. So the first test is that if we consider the transportation table to have m rows and n columns, then the number of allocations should be equal to m plus n minus 1. Now in our case, m is 3 because we have 3 rows, and n is 4 because we have 4 columns, and this minus 1. So this is equal to 3 plus 4 is 7, 7 minus 1 is 6. Now let's find out the number of allocations. So 1, 2, 3, 4, 5, 6. So number of allocations are also 6. So this condition has passed. The second condition is that the allocations should be in independent positions. So allocations should be in independent positions. So what this means is that it is impossible to travel from any allocation back to itself by a series of horizontal and vertical jumps from one occupied cell to another without a direct reversal of the route. So let's try for the cell BS. Now from BS, the next occupied cell where it can go to is CS. From CS, it can go to CR or CP. Now if we go to CR, then the only cell we can go from here is AR, and then from AR there is no way we can make a horizontal and vertical jump to BS. So we can say that the allocation for BS is in independent position, which also means that it is not possible to change the allocation without either rearranging the positions of the other allocations or violating the capacity and demand constraints. Similarly, if you evaluate all the other allocations, you'll find that all the allocations are in independent positions. So our second condition is also met. So this solution has passed the test for acceptability, and now we can proceed to test for optimality. So next is test for optimality. Now the first step to test for optimality using the modified distribution method is to set up a cost matrix containing the unit costs associated with the cells for which allocations have been made. So first we'll take the cells where the allocations have been made. So in our case the table will look like this. So what I've done is I have noted down the unit costs associated with the cells for which allocations have been made. So for example, AQ, AR, BS, CP, CR and CS. Now the next step is to assign the variable UI, where I is equal to 1, 2, 3 and so on, to each of the rows, and VJ, where J is equal to 1, 2, 3 and so on, to each of the columns. So this becomes U1, U2 and U3, and for the columns V1, V2, V3 and V4. Now the next step is to compute the values of U and V for the stone squares, or the squares which have allocations, such that UI plus Vj is equal to Cij, where Cij is the cost for the square. So UI plus Vj is equal to Cij. And since there are m plus n variables, so m plus n means there are 3 rows and 4 columns and 7 variables, but the allocations are m plus n minus 1, so we can assume the value of one of the variables as 0. So here we'll assume the value of V1 as 0. So let's find out the values of UI and VJs. So we have cell, and then UI plus Vj is equal to Cij, and then from this we'll find the values of UI and Vj. So we have the stone squares as AQ, AR, BS, CP, CR and CS. For AQ, UI is U1 and VJ is V2 and Cij is 3. So U1 plus V2 is equal to 3. For AR, UI is U1 and VJ is V3 and Cij is 11. So U1 plus V3 is equal to 11. For BS, UI is U2 and VJ is V4 and Cij is 1. So U2 plus V4 is equal to 1. For CP, UI is U3 and VJ is V1 and Cij is 5. So U3 plus V1 is equal to 5. For CR, UI is U3 and VJ is V3 and Cij is 15. So U3 plus V3 is equal to 15. For CS, UI is U3 and VJ is V4 and Cij is 9. So U3 plus V4 is equal to 9. Now we have to find the values of UI and VJ from these equations, and we have assumed that V1 is equal to 0. So let's note that down. So V1 is equal to 0. So let's put that value of V1 in this equation for CP. So what this means is that U3 is equal to 5. Now we have the value of U3. So let's put it in this equation. So 5 plus V3 is equal to 15. So that becomes V3 is equal to 15 minus 5. We'll take the 5 on the other side. So minus 5. So V3 is equal to 10. So U3 is equal to 5 and V3 is equal to 10. Now again, for this equation, U3 plus V4 is equal to 9. U3 is 5. So V4 is equal to 9 minus 5, which is 4. So U3 is equal to 5 and V4 is equal to 4. Now let's go to this equation for BS. U2 plus V4 is equal to 1 and we know V4 is equal to 4. So U2 plus 4 is equal to 1, or U2 is equal to 1 minus 4, which is minus 3. So U2 is equal to minus 3 and V4 is equal to 4. Now for this equation for AR, we know the value of V3, which is 10. So U1 is equal to 11 minus 10, which is 1. So U1 is equal to 1 and V3 is equal to 10. For the cell AQ, U1 plus V2 is equal to 3. We know that U1 is 1. So V2 is 3 minus 1, which is 2. So U1 is 1 and V2 is equal to 2. So let's note down these values of UI and VJ in this table. So U1 is 1, U2 is minus 3, U3 is 5, V1 is 0, V2 is 2, V3 is 10 and V4 is 4. Now in this step we calculated the value of UI and VJ using the stone squares, that is the squares which have an allocation. Now the next step is to calculate the net cost change for each water square, that is the squares which do not have any allocation. And the net cost change is equal to Cij minus UI plus Vj. And in this case, Cij is the cost of the water squares So Cij is known as the actual cost and Ui plus Vj is known as the implicit cost. So these were the stone squares, that is AQ, AR and so on. Now let's do the net cost change for the water squares. And then we have to find the value of net cost change, which is Cij minus Ui plus Vj. And we'll note down the net cost change in this column. Now let's note down the values of Cij for the water squares in this table. So this is 2, this is 7, this is 1, 0, 6 and 8. So now let's note down the water squares. AP, AS, BP, BQ, BR and CQ. Now for AP, that is this one, the value of Cij is 2, U1 is 1 and V1 is 0. So this becomes 2 minus 1 plus 0. For the square AS, value of Cij is 7, Ui is 1 and Vj is 4. So we get 7 minus 1 plus 4. For BP, the value is 1 minus 3 plus 0. For BQ, 0 minus 3 plus 2. For BR, 6 minus 3 plus 10. And for CQ, 8 minus 5 plus 2. So now let's calculate the net cost change. So this becomes 2 minus 1, which is 1. This is 7 minus 5, which is 2. This becomes 1 minus 3, or 1 plus 3, which is 4. This becomes minus and into bracket minus 1. So minus minus plus, this becomes 1. Now let's calculate the bracket here first. So 10 minus 3 is 7. So 6 minus 7 is minus 1. In this case, 8 minus 7 is 1. So here we still have a square BR which has a negative net cost change. This means that the optimal solution has not been reached. So now let's again perform these steps to improve the solution in order to move towards optimality. So this is the transportation table that we have achieved after the first iteration, and in the previous steps we concluded that this is not yet the optimal solution. However, it did help us reduce the cost from the initial feasible solution by 100 rupees. So now we'll again try to improve this solution. Now the first step in improving the solution is to select the water square with the largest negative net cost change. Now as per the previous step, we had found that BR is the square which has the negative net cost change. So we'll select this square. So this is the square. The next step is to subtract the smallest of the figures from each square at the negative sign on the closed path and add to each square at the positive sign on the path. So let's first build the closed path for this water square BR. So the closed path will be BR to CR, CR to CS, CS to BS, and BS to BR. And in this closed path we will assign alternate plus and minus signs, starting with a plus sign at the water square. So BR gets a plus, CR gets a minus, CS gets a plus, and BS gets a minus. Now subtract the smallest of the figures from each square at the negative sign on the closed path. So the smallest figure between BS and CR is 1. So we'll subtract 1 unit from BS and CR and add 1 unit to BR and CS. So this becomes 0, this becomes 2, this becomes 1, and this also becomes 1. And the next step is to prepare the new transportation table and check for optimality. So this is the new transportation table that we have achieved after making changes to allocations here. So as you would note, BR now has 1 unit allocated to it. BS has 0 units. CS has 2 units. And CR has 1 unit. So this is our further improved solution. Let's quickly find out the total cost for this solution. So total cost is equal to 5 3s are 15 plus 11 1s are 11 plus 6 1s are 6 plus 7 5s are 35 plus 15 1s are 15 plus 9 2s are 18. So this is equal to 15 plus 11 is 26, 26 plus 6 is 32, 32 plus 35 is 67, 67 plus 15 is 82, and 82 plus 18 is 100. And since the unit cost is in hundreds, so we'll multiply this by 100. So our total cost is 10,000 rupees. Now the initial feasible solution that we had obtained using the Vogel approximation method gave us a total cost of 10,200 rupees, while after the first iteration we had arrived at a total cost of 10,100 rupees, and after the second iteration we have arrived at a cost of 10,000 rupees. So definitely there is an improvement in the total cost of transportation. Now let's find out if this solution is optimal or not. So before we test for optimality, first we have to test whether this solution is acceptable to proceed with the optimality test or not. So let's first do the test for acceptability. So the first condition is allocations should be equal to m plus n minus 1. Now m plus n minus 1 is 3 plus 4 minus 1, which is equal to 6. And let's count the number of allocations. So 1, 2, 3, 4, 5, 6. So allocations is also equal to 6. So this condition has passed. The second condition is the allocations should be in independent positions. So allocations should be in independent positions, which means that we should not be able to create a closed loop through the allocated cells using horizontal and vertical lines without reversing the route. So if you check, all the allocations are in independent positions, so this condition is also met. So now let's move to the next step, which is to test for optimality, and we'll use the modified distribution method to test that. So test for optimality. So the first step in testing for optimality is to set up a cost matrix containing the unit costs associated with the squares for which allocations have been made. So in our case, this is how the matrix looks like. Now the next step is to assign the variable ui, where I is equal to 1, 2, 3 and so on, to each of the rows, and vj, where j is equal to 1, 2, 3 and so on, to each of the columns. So u1, u2, u3, v1, v2, v3, v4. Now the next step is to compute the values of u and v for stone squares such that ui plus vj is equal to cij. So stone squares, and then ui plus vj is equal to cij, and from this equation we'll find the values of ui and vj. So the stone squares in our case are AQ, AR, BR, CP, CR, and CS. Now for AQ, UI is U1 and VJ is V2. So U1 plus V2 is equal to 3 because Cij is 3. So U1 plus V2 is equal to 3. For AR, UI is U1, VJ is V3, and Cij is 11. So U1 plus V3 is equal to 11. For BR, UI is U2, VJ is V3, and Cij is 6. So U2 plus V3 is equal to 6. For CP, UI is U3, VJ is V1, and Cij is 5. So U3 plus V1 is equal to 5. For CR, UI is U3 and VJ is V3 and Cij is 15. So U3 plus V3 is equal to 15. In case of CS, UI is U3 and VJ is V4 and Cij is 9. So U3 plus V4 is equal to 9. Now here we are assuming that the value of one of the variables is 0. So V1 is equal to 0. And now let's use this value of V1 to find out all the values of UI and VJ. So let's first take CP because it has V1 and we know the value of V1. So in case of CP, U3 plus V1 is equal to 5 and V1 is 0. So U3 is equal to 5 and V1 is equal to 0. Now for CR, U3 is 5. So V3 becomes 15 minus 5 or 10. So U3 is equal to 5 and V3 is equal to 10. In case of CS, again U3 is equal to 5 and V4 is 9 minus 5, which is 4. So V4 is equal to 4. Now let's put the value of V3 in the case of BR. So V3 is 10. So U2 becomes 6 minus 10, which means U2 is minus 4 while V3 is equal to 10. Now let's put the value of V3 in this equation for AR. So V3 is 10. U1 is equal to 11 minus 10, which is 1. So U1 is equal to 1 while V3 is equal to 10. Now let's put the value of U1 in the equation for AQ. So U1 is 1. So V2 becomes 3 minus 1, which is 2. So U1 is 1 and V2 is equal to 2. So here we have found out the values of Ui and Vj. So let's put the values here in the table. So U1 is 1, U2 is minus 4, U3 is 5, V1 is 0, V2 is 2, V3 is 10 and V4 is 4. Now the next step is to calculate the net cost change for each of the water squares. So in this step we found out the value of Ui and Vj using the cost of the stone squares. And now we'll use these values of Ui and Vj to find out the net cost change for the water squares. And the net cost change is equal to Cij minus Ui plus Vj. Cij is the actual cost of the cell and Ui plus Vj is the implicit cost. So let me note down the unit cost of the water squares. So for AP it is 2, for AS it is 7, for BP it is 1, for BQ it is 0, and for BS it is 1, for CQ it is 8. So now let's find out the net cost change for the water squares. So water squares and then Cij minus Ui plus Vj, and this will give us the net cost change. So the water squares are AP, AS, BP, BQ, BS and CQ, and let's plug in the values of Cij, Ui and Vj. So for AP the value of Cij is 2, Ui is 1 and Vj is 0. So this becomes 2 minus 1 plus 0. Similarly for AS it is 7 minus 1 plus 4. For BP it is 1 minus 4 plus 0. For BQ 0 minus 4 plus 2. For BS 1 minus 4 plus 4. For CQ 8 minus 5 plus 2. Now let's calculate the value of net cost change. So this becomes 2 minus 1, which is 1. This becomes 7 minus 5, which is 2. This becomes 1 minus 4, so 1 plus 4, which is 5. This is 0 minus 4 plus 2, so minus 4 plus 2 is minus 2. and minus 2 multiplied by minus 1 is 2. So this is 2. For this one, 1 minus 0, so 1, and here 8 minus 7, so this is 1. So here we have all the values of net cost change as positive values. So what this means is that we have already arrived at the optimal solution. So the solution where we had arrived at a total cost of 10,000 rupees is the optimal solution, and the transportation cost for that solution is 10,000 rupees.